Everybody, this is similar to an SMO, that's Singapore Math Olympiad junior level problem. Junior back, gosh, I don't have the exact date, maybe around 2014, something like that. Now this one's slightly harder in the sense that the polynomial is not already factored. I think most of you probably see why that's important already. But we're looking for the smallest positive integer m such that this fifth degree polynomial, quintic I guess, is divisible by 1073. Now something that turns out to be important, and this isn't in the name of this, but I'll just tell you right now, this is 29 times 37, and it makes it a lot easier. It's a semi-prime number. It's the product of two prime numbers. They call it semi-prime. And it makes it slightly easier to process it. Like if you just know this, you don't even have to know that the Hindu-Arabic expansion is 1073. Okay, now, first thing to do, and it's rarely a bad idea, is to factor out an m, all right? And this automatically tells us that m equals 0 is one of the roots. And of course, that makes it a factor. Now also from Vieta's formulas, and I won't go through the derivation of that, but minus 10 presents as the sum of the roots, okay? The sum of the roots. You see the 10 here and the 10 here, the coefficient of one less than a degree, that term always presents as the negative sum of the roots. And again, I won't spend the time to try to develop that, but it's a result that's well known. And also the product of the positive roots, of course, I mean the product of the non-zero roots. Let me put non-zero parenthetically here. So not equal to 0, of course. I'm just saying it to be clear. Okay, so we have these two constraints on the roots. They sum up to negative 10, okay? And they also have a product of 24, so they can't be that large. For example, 12 and 24 won't be roots because they would sum up. They would sum up to something greater than 10. Maybe you could have some offsetting stuff going on, but you can more or less forget about 24 and 12 as possible roots. Okay, now that's not rigorous. It's just me waving my hands. But in any event, what we get here is negative 10. Is 0 is the corresponds to m equals 0, right? And then 1 plus 2 plus 3 plus 4 is 10, okay? Now there's a uniqueness about polynomials. One, if you find some roots, that's it. You don't have to worry about, and I'm saying that a priori there might be other combinations that would yield negative 10 and 24 of the roots. I'm not sure, but a priori you can't just wave your, I am waving my hands here, but you can verify that 1, 2, 3, and 4 are roots if you want to. I'm not going to go through that on this video, okay? But 1, 2, 3, and 4 are indeed roots. But I'm not claiming that I went through this rigorously. There may have been other combinations a priori, okay? Now, so we get this factorization right here. This would be for m equals negative 1 right here, okay? M equals negative 1 would be the 0 corresponding to this root, m equals negative 2, and so on. So you see we have a nice factorization, and that's useful because we just need to find out when multiples of 29 and 37 appear and what the smallest values are. So what I'm going to do towards that is just list the multiples of 29 and 37 and see if we can notice anything that will be close together, so to speak. In other words, the roots have to be within 5 of each other, okay, within 5 integers of each other, all right, just by this factorization. So let's go ahead and get started on that. And again, I'm just going to do it slow in plotting. I'm going to write down the multiples of 29. Okay, what do we have? 29, 58. And it's hard to know how far to go. And then over here I'll do the 37. 37, the next multiple of 37 is 74. Okay, and let's see, the next multiple of 29 would be 87. Just adding 29 at a time. Okay, right here, what do we get? If you add 37 to that, what do we get? 111. 111. 3 times 37 is 111. All right, now you see we're looking for these guys being close to each other. So far they're not close, right? 37 is not close enough to 58 to be within 5, right? And the same thing here, 74 and 87 is getting a little closer, but it's still not within 5. Okay, so let's keep plotting along here. The next one here would be what, 116. Okay, now you see right here we're pretty close, but we're 5 away. Would that work? I don't think. Let's see, that's too far away, isn't it? I think 116 and 111. Did I do this right? 29 and 87 is 116. Okay, 111. Let's keep writing stuff down here. 37 right here would be 148. I think this is not quite close enough, right? Because if you put 116 right here, right, what would this be? 116. That's not close enough, I don't believe, is it? But what this next one is without a doubt. Let's see here, 29. That's 145. Now we're definitely in business here with 145, right? Because you see how 148 is a multiple of 37 and 145 is a multiple of 29, and they're 3 apart. Okay, so you see what you can do. You want to put your largest number as far to the right as you can. So we would have to associate 148 right here, right? And then what would that make this? 148, so that would make this 144. Right, folks? Yeah, so you see, folks, this one wasn't quite close enough. Okay, so you got 144 for M, right? And then 144 plus 4 is 148. Okay, well, why is that special? Well, we got our 29 and 37. This is a multiple of, well, okay, 140, let's see, 148. Yeah, okay, 148 would give us our multiple of 37, right? That's 4 times 37. Yeah, let's be a little more careful about this. And then right here, our M plus 1 would be 145, right? Yeah, this is getting it done, isn't it? Okay, this is 145, but 145 is a multiple of 29, namely 5 times 29. Okay. So you see there, we got it going on. We got 37 and 29 as factors of this 5-term factorization, but 29 times 37 is the divisibility constant of 1073 we were interested in, right? And this clearly is the smallest. This came close, right? But y'all check it out. If you put 116 here, it's not going to work out. That would put 112 right here, right? That would put 112 right here. And we would miss our multiple of 29, right? Okay, so this was pretty close, 116 and 111, but 148, 145 is definitely within range. And so our answer here is M equals 144. Okay, and you can imagine how large this number would be. If you look at the factorization, you would have 144 times 145 times 146 times 147 times 148. The power of this method is we don't even have to know what that is. We've demonstrated that it is a multiple of 1073. Moreover, we've demonstrated that M equals 144 is the smallest positive integer that takes care of that condition. Okay, so we're done with the problem, folks. Let me know what you thought. And I admit I waved my hands just a little bit right here, but the minus 10 and the 24 gives us enough conditions to at least try this. And again, I wouldn't know in advance if those work, but you can check at least, and you can go back and check to see that this factorization does yield these coefficients of 10, 35, 50, and 24. Okay, but again, M equals 144 is the solution to this problem. And just one last comment. The SMO Junior problem back in, I think, 2014, they just gave it to you already factored, like n times n plus 1 times n plus 2. But I used the same idea in methodology that they espoused in their solution that all the Chinese guys published and posted that nice solution manual, So that's what I was doing. I used their technique, but I just made the problem slightly more of a challenge in the sense you had to come up with a factorization of a fifth degree polynomial vis-a-vis a third degree polynomial. But anyway, here's your solution, 144. Thanks for viewing.